So this is the beginning of our unit on solutions chemistry for Regents Chemistry. Again, I am Mrs. Davis. I welcome you. You should have the notes open for your notes book. And we're going to get started talking about what is a solution. So some of this will be a review from our matter and energy unit from the beginning of the year. So we're going to start off by talking about mixtures. We have two kinds of mixtures. We have a homogeneous mixture and we have a heterogeneous mixture. Let me just move my, there we go. So heterogeneous and homogeneous. So if you remember your prefixes, right, the prefix homo means the same and the prefix hetero means different, right? So we have something the same, something different that deals with a mixture. And so remember, a mixture is not a pure substance. So let's just make sure that we have down here. So this is not a pure substance. And the proportions can vary. And what does vary mean? That means I can change the proportions, right? I can have a little bit of this and a little bit of that, or a lot of this and a lot of that, or a little bit and a lot. So the composition of a homogeneous solution, or homogeneous, right? You can say it either way, is uniform, right? All the way the same throughout. So there's no visible differences when you're looking at a homogeneous mixture. It's going to be completely transparent as well. It means you're not going to see any visible differences in the mixture. So now the opposite of that is going to be heterogeneous, right? Which means different. That means it's not uniform. It's going to be opaque, or you might see stuff kind of floating in there, or maybe settling to the bottom, right? So you're going to see like either solids floating around in a liquid. So it's not uniform. It's going to be different composition throughout, not uniform. So all solutions, right? The term solution means a homogeneous mixture. It is not a pure substance. It is a mixture, transparent, that is the uniform all the way throughout. You cannot filter. That means if you pour the solution through a filter paper, right, like a paper towel or a coffee filter or a lab filter, if you're working in a lab, everything is going to pass right through the filter and you're not going to be able to separate the components of your mixture. So for example, saline, right, salt water, and I'm going to write down over here solution, right? If you see NaCl, which means salt, right, sodium chloride, and an AQ, you just by seeing those four letters together combined means salt dissolved in water. It is an aqueous solution. That means automatically it's homogeneous. It's all the way the same throughout. It's transparent. Every particle of sodium chloride is evenly distributed the same throughout the whole mixture. And if I were to pour salt water through a filter, it's still going to be salty water when it passes through the filter because there's nothing to filter away. So now let's talk about our heterogeneous mixtures. So an example would be a colloid. A colloid is a type of heterogeneous mixture that you cannot filter. So example, mayonnaise is a colloid, and so is milk, and so is fog. If I pour milk through a filter paper, milk is not necessarily a homogeneous solution because it's not, right? There's little, you can't really see it, but it's cloudy, right? You can't see through it. So that's going to make it a heterogeneous mixture. And we have the ones that we can filter versus the ones that we can filter. So I cannot filter mayonnaise. First of all, it's really thick. It's not going to flow through the filter paper. But over time, if it fell through the filter paper, you're not going to be able to separate out the egg and oil that's whipped together to make the mayonnaise. So if I have a suspension, I can filter. That means that there's particles suspended in the solution. So example, muddy water, right? If I pour muddy water through a filter paper, I'm going to get the clear water, and then I'm going to get, the mud is going to get trapped in the filter. So this is kind of like, you know, if you have a kitchen filter at home, like a Brita filter, you're going to be able to filter out solids because they're going to stick in the filter. The particles are too big to fit through the little holes in the filter paper. So then you're gonna be able to separate the solids from the liquids. Another great food example is mustard, is a suspension, and actually so is ketchup. Have you ever taken mustard and then you go to put mustard on a hot dog or mustard on a sandwich, and all of a sudden it just like blurps out some clear liquid, and you're like, what? That's not even my mustard. You have to shake up the mustard container. Well, that's because mustard is a suspension, and if you let it sit for a long time, all of the mustard solids, right, which is what makes mustard, right, because mustard is actually a solution, it's a suspension. So then it settles to the bottom. So a suspension is going to settle, like muddy water will settle, and so will orange juice with pulp, right? The pulp is going to settle down to the bottom, but if I wanted to get rid of, I could always just pass it through a filter paper. So another great example is if I have sand and if I have salt and water, if I have all three of those things mixed together, I have a heterogeneous solution between the sand and the salt water, but then the salt water itself is a homogeneous solution. So I would be able to separate those components of this mixture, right? Mixtures can be separated by physical means. If I needed to separate sand and salt water, right, I would pour the sandy salt water through a filter, right? Because then the particles of the sand are too big to pass through the holes of the filter. So then that's going to catch all of the sand particles. And then in the bottom, I'm going to have salt water. And now if I want to get rid of the salt in the water, right, well, not get rid of, if I want to separate those two, I can evaporate away the water, or I can make evaporation happen faster by boiling the water, and then I'm left with salt. So now let's talk about what are parts of a solution. So we have two terms that are very similar. We have solute and solvent. So the solute is the substance that is being dissolved. And most of the time in this course, we're going to be talking about that as a solid, right? So if I'm talking about salt water, salt would be the solute. That's what we're dissolving in the water. So sugar and salt are great kitchen examples of solute. And now the solute gets dissolved in the solvent. And the solvent is the substance that dissolves the other substance, and many times this is going to be a liquid. So in our example with the salt water, right, water dissolves the salt, or water dissolves the sugar. And then we have a solute and the solvent, right? And big V, little u. That means the solute is usually going to be the smaller amount of the substance. So the smaller amount. I remember if there's two M's in amount because I'm a terrible speller. A solvent is the larger amount. So if I'm making some salty water, or if I'm making some sugar water, the water is going to be the larger amount compared to the solid that I'm trying to dissolve. Which leads us to our types of solutions. We have gas solutions, where gas is the solvent. So if you think about the air around us is a solution. The air around us is a mixture of gases. It's homogeneous, right? You cannot see oxygen, you cannot see the nitrogen or the carbon dioxide or the water vapor or the methane gas or any of the other components of the air, right? So we have nitrogen is the larger amount of our of the air that we breathe, right? So that's why nitrogen is considered our solvent. And now we have oxygen and carbon dioxide, and of course there's other gases there as well, but that's just to give you an example of a solution that's air made up of gases. It doesn't have to be liquids all the time. And so we have solutions that are considered to be solid, where solid is the solvent. And now this example is bronze, which is an alloy. It's not a pure metal. Remember, solutions are mixtures still, where the proportions can vary. So it is not a pure substance. So bronze is not a pure substance. Bronze is composed of copper, tin, and zinc, and it's an alloy, and the proportions between these three things can vary, but the larger amount is going to be the copper, so we call copper the solvent. And then tin and the zinc are going to be these solutes. We are more familiar with liquids. So where liquid is the solvent, right, Kool-Aid, right, which is, you know, the sugary drink with lots of color, that's going to be our solution. And water is the solvent. So I take the powdered Kool-Aid, I add water. Water is the solvent. Water does the dissolving of the powder, which is the solute. Okay, so the solute. Remember, since this is a recording, then you can go back and rewind and pause, to get the notes, and they are also provided to you in Google Classroom. All right, so let's take a look at the rate of solution. So let me just move this bar over here at the top. Let me just move that down to the bottom, I think. So we have the rate of solution. What does rate mean? Of course, now that I did that, that means now I'm messing up. I'm just going to go put that back up there because it messed up things. The rate of solution. All right, make sure I still have my pen going here. Okay, so anytime you have the rate of something, rate means change over time, right? So we have interest rates, right? So that's the amount of interest you're charged over time. When you drive on the highway, if the speed limit is 65 miles an hour, that's a rate, 65 miles over 1 hour. And so the rate of a solution is how fast the solute is dissolving the solvent over time. So the less time it takes to dissolve something, the faster the rate, right? So just like if I drive 70 miles an hour is faster than 65 miles an hour, right? I can get somewhere in less time, but don't speed. Please be a safe driver. All right, so what affects the rate of something dissolving? Some of these are intuitive. Particle size. So if I decrease the size of the particle, right? So this means decrease, right? If I decrease the size of the particle, that means I increase the surface area contact between my solute and my solvent. So then that increases my rate of solution. So an example of that is if I crush up a chunk of salt and I grind it up into a very, very fine little powder, and I grind that up, all of those particles have more surface area contact with the water trying to dissolve it, so it will dissolve faster. Right, so granulated sugar or salt is going to dissolve faster than a cube. Right, if I just drop a cube of sugar into some room temperature water, it is not going to dissolve as fast as if I had a tablespoon of sugar. The same equivalent size, if it's all dispersed with little particles, is going to dissolve much faster, right? So when you grind something up and you crush it up into smaller pieces, you're increasing the surface area contact between the solute and the solvent. Right, so here's our sugar cubes versus granulated sugar, right? So then that's going to make something dissolve a lot faster if I have smaller little pieces to dissolve. So the second thing we can do to increase the rate of solution, which means the rate of dissolving, is by stirring. If you have iced tea and you want to add some sugar to that, you put the sugar packet in, right? You're at the restaurant, you open up and you stir it around with your spoon or with a straw, right? Because by stirring, right, and then the faster you stir, the more vigorous you stir, you're increasing the stirring, increases the amount of collisions and again, contact, right? If two things don't come in contact with each other, there's no way they're going to dissolve between the solute and the solvent, and then that increases the rate of solution, right? So if you're stirring your coffee, why do we stir coffee? You just stir it because you're like, oh, I just put sugar in and I just stir. No, you stir it because you're trying to dissolve the sugar, right? And when you stir it, you kind of make it swirl around, and then now you're having more contact between the hot coffee and the sugar. And so now the next thing we can do is we can affect the rate of solution with temperature. So now my sugar in this hot coffee is going to dissolve a lot faster than sugar in a cold coffee. And so if you're a Dunkin' Donuts fan, right, also they have the liquid sugar, right? A lot of you ask for liquid sugar when you get your coffee because it dissolves better, right? Especially in an iced coffee, right? The crystals take a lot longer to dissolve and sometimes they settle down to the bottom if they don't dissolve all the way. So now if I increase the temperature, the molecules move faster. So then that increases the collisions. And again, that's the surface area contact between our solute and our solvent. and then we increase the rate of our solution, right? You just, oh wait, I have to dissolve like a whole bunch of sugar. Well, I better just heat that all up, and there you go. Now, if I combine things, grind it all up into a small particle size, heat it up, and stir. Now you're going to have the fat. That's how I would get the fastest way to dissolve. So things dissolve faster in hot water. If I tried to dissolve a packet of sugar in hot tea versus cold tea, right? It's intuitive. We've had experience with that, right? Hot tea, right? So now this is a solution, right? Can you see the individual little sugar particles in there? No. In this black coffee up here, can you see the sugar? No. So those would be homogeneous solutions. And now the last factor that's going to influence how fast something dissolves, all right, our rate of solution, right, change over time, is the amount of solute already in the solution. If I have coffee and I already have a lot of sugar in it, and I want to keep adding sugar, it is not an infinite amount of sugar that you can dissolve in a cup of coffee. Or if I'm working with lab chemicals, right, there's just not an infinite amount that in a specific amount of volume of water. So if I increase the amount of solute, right, meaning add more stuff, right, more sugar, more salt, more whatever chemical we're talking about, I decrease the ability of the solvent to dissolve because it's already got a lot of stuff in it. So then that means it decreases the rate of solution. So that first packet of sugar is going to dissolve faster than the 8th packet of sugar. Oh, and by the way, cut down on the sugar on the coffee. That's my 2 cents for the day. 2 cents for the day. Okay, and that's where we are going to stop for today, and we'll pick up your next set of notes shortly. If you have any questions, please make sure you reach out to your teacher and make sure that you're reading very carefully. All right, until our next set of notes. All right, thank you, and goodbye.